Today we're talking about absolute value. I know we previously reviewed the meaning of absolute value and how to calculate it, but today we're talking about absolute value as a function, how it performs over the full domain and what the graph of it will look like. So really quickly we can review absolute value and what are the things that absolute value is. We remember that it is always positive. It represents the distance from zero because distance, it represents distance, and that's why it's always positive. We show it with these vertical lines, right? That would be read as the absolute value of x. And then lastly, if x is negative, right, so if x is less than 0, then the absolute value of x just equals the opposite of x. And we reviewed this when we were talking about how to solve it. If x is greater than 0, then the absolute value of x just equals x. It doesn't change anything else about the input except to make the value positive, right? It's only measuring that distance from 0. So if we review absolute value, let's also talk for a second about what a function is. So a function is really just a relationship between two terms. And you remember a function has to be one-to-one. So every input has one output and exactly one output, only one output. That's just the definition of a function. And we've looked at lots of functions. In general, we talked about functions. Most of the ones that we've worked with have been straight lines, but we talked about that a function can look like anything as long as it never happens that there's more than one output for any given input. So we've had examples of functions that look in lots of different ways. And these three examples that I drew can help us to discuss continuous versus discontinuous. We've used these words, and to some extent they're self-explanatory, but let's look at what it might mean. I'm going to draw one more here. This is actually the absolute value function that we're going to get to today. A continuous function has no breaks, for one thing. It has no breaks. And it kind of, the change is predictable. It stays the same. A discontinuous function will have a break in it. It'll have something like a hole, a break somewhere in it. So for example, this second function that I drew would be an example of a discontinuous function. Later in the chapter, we're going to get into step functions that look like this. These would be examples of discontinuous functions, or even just a piecewise function, maybe something that looks like this. Even that could be considered a discontinuous function because it has two different definitions over the domain. So it's just some vocabulary. Now let's go ahead and look at what does the graph of an absolute value function look like. So we talked earlier about parent functions and the fact that if we know the basic behavior of a family of functions, then we know we can use that to define any function within that family. So the parent function for absolute value is f of x equals the absolute value of x. And its graph looks like this blue V that I've drawn. Because if you remember, if you go negative in the x, the absolute value is just the opposite of the number. So if I put in -1, I get 1. If I put in -2, I get 2. Right? In the positive x domain, every number that I put in for x, I get out the same number for y. So just as a note, and it will become more important later, this half of the function looks a lot like f of x equals x, and this half of the function looks an awful lot like f of x equals -x. So for the negative domain, right, where x is negative, there's a negative slope. The absolute value is decreasing. At 0, the behavior of the function changes, and for the positive domain, it has a positive slope. It's increasing. Now, I've been using this word domain. Remember, that's just the numbers you can put into a function. And if you notice, I can put any number for x in that I want to. Any x value can go in. It can be negative. It can be positive. There's no limit. So the domain of the absolute value is all real numbers. The range, though, is different. The range is what I get out. And if you look at this function, I can put in any number I want, but all of my answers, all the results, everything I get out, it's always positive. So the range is positive numbers. And they can write this several ways, positive real numbers. Sometimes they write y is greater than or equal to 0. F of x is greater than or equal to 0. But you see the domain, I can put anything I want in, but for the range of the parent function, right? The range of the parent function, this basic absolute value function, is positive numbers. So the reason I emphasize that parent function is, remember, I can always change it. I can always change my function around by performing operations on it. So if g of x equals twice the absolute value of x, how does that compare to the general parent function f of x equals the absolute value of x? So let's go ahead and just draw in our parent function. And remember, in this case, 1 equals 1 and negative 1 equals 1, right? My lines are defined by that negative x and positive x, slope of 1 for my parent function. But what happens if I take this new function, g of x equals twice the absolute value of x? There's a couple of ways you can look at this. One is you could just make a table, x, g of x, g of x. If I put 0 in for x, well, the absolute value of 0 times 2 would give me 0. If I put in 1 times 2 would give me 2. If I put in 2, absolute value of 2 is 2, I'd get 4. I better check some negative numbers too. If I put in negative 1, well, the absolute value of negative 1 is 1 times 2, that would give me 2. So I could make a table to graph it. Another thing I do is I can remember that function transformations, and we will do more of this later in the chapter, but I can remember those function transformations that we did a few topics ago. And if g of x equals twice f of x, right, which is what we have here, then that's a vertical stretch. I'm going to take it and pull my function straight up, and that ends up narrowing the function. It increases the slope. Doing it this way might also help you remember that that doesn't change the domain. So either way, let's go ahead and look at the graph. It still sits at 0, 0, but 1 now becomes 2. 2 becomes 4, right? So it becomes a much steeper V, still symmetric about the y-axis. So that's what the graph would look like. And then if you remember, the question is, how do the domain and range compare? Let me make this page a little bit longer. So if I have f of x and g of x, let's look at the domain and range. So for f of x, we said on the previous slide, the domain of the parent function is all real numbers and the range is all positive numbers. So I can just go ahead and write those in. And then let's look at g of x. Can I still put anything I want in for x? Is there anything in this graph or in my knowledge that makes me believe that I'm going to limit where I can put the x's? And there isn't. There's nothing in there. The domain does not change with a vertical stretch. And how about the range? I can look at my graph and see that as this continues, it will continue to go up. As this continues negative, it will continue to go up. So in fact, my range is also unchanged. As you look at the answer keys in Pearson, that is what they say. The range is unchanged, but you need to do both, list unchanged and just emphasize that that means that y is greater than or equal to 0. So let's look at one more example here. I'm going to start by sketching in our parent function, f of x equals the absolute value of x. It is just a standard, the v right there. And then let's go ahead and look at this one. h of x equals negative absolute value of x. I don't know what that was. Okay. H of x equals negative absolute value of x. So if I look at this as a function transformation, I see that this negative sign should give me a reflection, right? So what I would expect is a reflection. It's going to flip it, right? Everything that I would expect to get out from the parent function, it's -1 times my parent function. So everything that I would expect to get out, I'm actually going to get out the opposite. With that information, I should be able to sketch it. The opposite of 0 is 0, the opposite of 1 is -1, the opposite of 2 is -2. And going this way, the opposite of 1, opposite of 2 is. So this is what I would expect. Just for practice, we can also make a table, x and h of x. 0, negative absolute value of 0 is still 0. If I put in 1 for x, the absolute value of 1 is 1. The opposite of that is -1. 2, absolute value of 2 would be 2. The opposite of that is -2. If I put in -1, the absolute value of -1 is 1, but the opposite of that is -1. So you can see it does match this graph that we sketched based on our knowledge. So I don't really care which way you graph these. If you use your function transformation knowledge, you use a table. There are IXLs to practice that do require the table. But either way, for these problems is fine. So let's look again. How do they compare? So let's list our parent function and our modified function. I'm doing this, I think, the opposite way I did it before, but that's okay. We will work it out. The parent function, my domain, is all real numbers, and my range is y greater than or equal to 0. Okay. For h of x, my domain is unchanged. I think you will discover as we go through, it is very hard. You cannot alter the domain of the absolute value function without adding another function. Most of these, the domain will be all real numbers until you start to get more complicated and add other things in. But how about the range? This time, if I look at these red lines, it looks like they're going to continue going in the same direction. So as x continues to get big, the range is just going to get increasingly negative. As x continues to get small, the function itself is going to get increasingly negative. So in this case, the range is reflected, and it is less than or equal to 0. It's all negative numbers in this case. So someone asked a question when we went over this in class. Can you do more than one at a time? And absolutely you can. So let's look at these. I know that the domain and range of my parent function. And I know that if I stretch them vertically, the domain is unchanged and the range is unchanged. If I reflect it with this negative sign, my domain is unchanged and my range is reflected. It becomes the opposite. So what happens if I combine this and I put the negative sign and the 2 there together? My domain clearly is still unchanged. But what about my range? In this case, the negative sign is going to win. And you can check that just by looking at a few things. Any positive number I put in, I'm going to get something positive out. Multiply a positive by a 2. Then I'm going to get another positive. When I take that positive number and multiply it by a negative, every time I will get a negative number out. So that's just one example of a combined transformation. I'm going to leave it here for now, and if you have questions, please come and ask.